If you enjoy calm, thoughtful science that helps you unwind, take a moment to like the video and subscribe. It really helps the channel find others who enjoy slowing things down, and if you feel like it, let me know where you're watching or listening from. A quiet room, a darkened train, a phone glowing softly beside the bed. Different places, separated by distance, but all sharing the same space in between. Tonight's question begins with something that feels obvious, almost too obvious to ask. When you look up at the night sky, or pause in a silent room, it feels as though there are gaps everywhere. Vast stretches where nothing is happening, nothing moving, nothing there. Space appears empty in the most literal sense, as though it is simply a backdrop, a dark canvas on which the universe places its stars, planets, and galaxies. But physics has a habit of gently undoing what feels obvious. Over the past century, scientists have discovered that even the emptiest regions of space are not truly still, not truly silent, and not truly empty. Energy persists where no particles remain. Subtle activity continues where nothing seems to exist. And the very idea of nothing turns out to be far more complicated than common sense would ever suggest. So tonight, as things slow down, the question is a simple one. Is empty space really empty? Emptiness feels like one of the simplest ideas the mind can hold. It rarely needs explaining. An empty glass is one without water. An empty room is one without people. An empty street late at night is one where movement has paused, sound has softened, and attention drifts. In everyday life, emptiness usually means absence. Something that could be there is not there. Something that was there has gone. This way of thinking feels so natural that it barely registers as a definition at all. Emptiness appears obvious, intuitive, almost self-explanatory. It is what remains when objects are removed. It is the space left behind when matter, sound, or activity withdraws. In ordinary language, empty means clear, vacant, unused, hollow, or blank. And for most practical purposes, that definition works extremely well. But even here, something subtle is already happening. When something is described as empty, it is rarely meant in an absolute sense. An empty glass is still full of air. An empty room is filled with light, warmth, and pressure. Even silence carries faint vibrations. Everyday emptiness is never total. It is always emptiness relative to expectation. This is where language quietly shapes intuition. Words like nothing, nowhere, and empty suggest absolute absence. They imply a kind of perfect void, a condition where there is truly nothing at all, no substance, no activity, no influence. But in practice, language is forgiving. It allows these words to be used loosely, without demanding precision. Science, on the other hand, is not so relaxed. When physics asks whether something is empty, it is not asking whether something looks empty or feels empty. It is asking a much narrower and more demanding question. Empty of what exactly? Empty of matter, empty of particles, empty of energy, empty of forces, empty of structure. Each of these is a different claim, and each requires a different kind of evidence. This is why emptiness becomes a scientific problem rather than a philosophical one. Philosophy may ask what nothingness means. Physics asks whether a region of space contains measurable properties or produces measurable effects. If it does, then it is not empty in the way physics defines emptiness, no matter how empty it appears to the senses. In classical physics, this distinction seemed manageable. Matter was made of particles. Energy was associated with motion, heat, or radiation. Forces acted through space, but space itself was treated as a passive stage. Remove the particles, and what remained appeared to be nothing of consequence. A background, a container, a silent arena where events unfolded but which did not itself participate. This view aligned neatly with everyday experience. If all objects are removed from a room, the room appears empty. If air is pumped out of a container, it is called a vacuum. The less matter present, the emptier the space appears to be. For a long time, physics followed this intuition without serious resistance. But even early on, careful thinkers noticed that emptiness was more complicated than it first appeared. Take air, for example. For much of human history, air was not considered a substance at all. It was invisible, weightless to the senses, and seemingly insubstantial. Only through experiments in the 17th century did scientists like Evangelista Torricelli and Blaise Pascal demonstrate that air has weight, pressure, and physical presence. What had once been treated as nothing turned out to be something measurable. This pattern repeats throughout the history of science. Each time emptiness is examined more closely, new layers of structure are revealed. Things once dismissed as absence become reclassified as subtle forms of presence. This does not happen because scientists enjoy complicating simple ideas. It happens because nature refuses to cooperate with intuition. At its core, the scientific question of emptiness is a physical claim. It is a claim about what exists in a region of space, and what does not. It is not enough to say that nothing can be seen there. Vision is limited. Instruments extend perception far beyond the senses, and they often detect activity where the eye sees none. If a region of space can exert a force, store energy, transmit motion, or influence matter elsewhere, then physics must treat it as something rather than nothing. This is why defining emptiness is the first scientific problem, not the last. Before any measurement can be interpreted, before any experiment can be designed, there must be clarity about what absence actually means. Otherwise, discoveries risk being misunderstood or dismissed simply because they do not fit the initial assumption of nothingness. Consider temperature as an example. Absolute zero is defined as the lowest possible temperature, where thermal motion reaches its minimum. It is not defined by intuition, but by precise physical limits. Similarly, emptiness requires definition in terms of physical quantities. What is the lowest possible energy state of space? What is the minimum level of activity allowed by the laws of physics? These are not questions of language, but of measurement and theory. There is also a psychological comfort in emptiness. It provides contrast. Objects feel more real when set against empty space. Motion feels meaningful when surrounded by stillness. The mind uses emptiness as a framing device. This makes it tempting to treat empty space as a neutral background, a passive absence that can be safely ignored. Physics does not grant that luxury. As understanding deepens, space itself begins to show properties. It resists compression, it bends, it stores energy, it fluctuates. None of this is obvious at human scales, and none of it announces itself loudly. But subtle does not mean insignificant. The challenge, then, is not to abandon intuition, but to refine it. Everyday emptiness is a useful starting point, but it cannot be the final word. Science must replace vague absence with precise definitions. Empty of particles is not the same as empty of fields. Empty of matter is not the same as empty of energy. And empty in one theory may not be empty in another. By slowing down and being careful with definitions, a deeper picture begins to form. Emptiness is no longer a single idea, but a spectrum of conditions. Some regions are emptier than others. Some forms of emptiness are achievable. Others are forbidden by the laws of nature themselves. Once definitions are clear, Evidence can be allowed to speak without confusion. Measurements can be trusted to mean what they say, and the quiet assumption that nothing means nothing begins to loosen, not through speculation or drama, but through careful, patient observation. Emptiness, it turns out, is not a destination reached after everything else is removed. It is a starting point. A question asked before understanding can move forward, and the moment that question is taken seriously, the idea of nothing becomes one of the most interesting problems physics has ever encountered. For most of human history, the idea of absolute emptiness felt not just unlikely, but deeply uncomfortable. The notion that there could be a place where nothing exists at all challenged intuition, logic, and belief all at once. Nature, as early thinkers understood it, seemed full by default. Motion happened because something pushed something else. Change occurred because substances interacted. To imagine a region with no substance, no resistance, and no cause felt less like science and more like contradiction. This discomfort did not arise from ignorance or superstition. It grew from a sincere attempt to make sense of the world using careful reasoning. Early natural philosophy was not careless. It was systematic, structured, and deeply invested in coherence. And within that framework, emptiness appeared to cause more problems than it solved. One of the most influential voices shaping this view was Aristotle. Writing in the 4th century before the Common Era, Aristotle argued forcefully against the possibility of a vacuum. His reasoning was not casual opinion. It was grounded in a broader system of thought about motion, causation, and the nature of matter itself. According to Aristotle, motion required a medium. Objects moved through something, not through nothing. If a vacuum existed, he reasoned, motion would become undefined. Objects would accelerate infinitely because there would be no resistance to limit their speed. This was not merely unlikely. It was logically unacceptable. Nature, in Aristotle's view, did nothing without reason, and infinite speeds had no place in a rational universe. This led to a principle often summarized as horror vacui, the idea that nature abhors a vacuum. While the phrase itself was coined later, the sentiment traces directly back to Aristotle's arguments. Emptiness was treated not as a neutral absence, but as a violation of natural order. Wherever space appeared empty, something must be filling it, even if it could not yet be identified. Aristotle's influence cannot be overstated. His work shaped scientific thought for nearly 2,000 years. Through the medieval period, his ideas were preserved, expanded, and integrated into broader belief systems across Europe and the Islamic world. Natural philosophy, theology, and logic became intertwined. Within this framework, questioning the impossibility of emptiness was not simply a scientific disagreement. It was a challenge to a worldview. This is where belief systems began to constrain scientific questions. If the structure of the universe was assumed to be complete, purposeful, and continuous, then emptiness had no place to exist. Asking whether nothing could exist was treated less as an experiment to be performed and more as a category error. The question itself was considered misguided. As a result, many early discussions of emptiness focused on why it could not exist, rather than how it might be tested. Arguments were built on logical consistency rather than measurement. Nature was expected to behave in ways that aligned with philosophical necessity. Evidence, when it appeared to conflict, was often reinterpreted rather than accepted at face value. There was also a practical limitation. Even if someone had suspected that emptiness might be possible, there was no reliable way to create it. Air was invisible and poorly understood. It was not yet recognized as a material substance with weight and pressure. Removing air from a container did not seem meaningfully different from sealing it. Without tools to manipulate pressure, emptiness remained an abstract idea. This combination of philosophical commitment and technical limitation kept emptiness at arm's length. Nature was assumed to be full because it had to be full. Any apparent gaps were treated as illusions or misunderstandings. The universe was imagined as a continuous fabric of matter, influence, and purpose, with no holes allowed. There is a certain gentle irony in this resistance. The fear of nothing was not fear in an emotional sense, but in a logical one. Emptiness threatened to unravel carefully constructed explanations. It introduced instability into systems built on balance and continuity. Rejecting the vacuum was a way of preserving order. And in fairness, the rejection worked remarkably well for a long time. Aristotle's physics explained everyday motion tolerably well. Objects fell, flames rose, heavy things behaved differently from light things. Within the scale of ordinary human experience, emptiness was not required to make sense of the world. But cracks began to form as attention turned toward more careful observation. Water pumps failed to lift water beyond certain heights. Suction behaved strangely. Pressure effects appeared where none were expected. These were not philosophical problems, they were practical ones. And practical problems have a habit of forcing new questions. Still, it took courage to ask those questions. Challenging the impossibility of emptiness meant challenging centuries of accepted wisdom. It required treating nothing not as an error, but as a hypothesis. That shift did not happen overnight, and it did not happen easily. What finally loosened the grip of this historical discomfort was not a sudden change of mind, but a slow accumulation of anomalies. Situations where existing explanations strained or failed. Moments when nature behaved in ways that could not be reconciled with the assumption of fullness. Once that happened, emptiness could be approached not as a forbidden idea, but as an experimental target, something to probe, something to test, something to create, even imperfectly. The fear of nothing began to soften, replaced by curiosity about what would happen if the assumptions were wrong. The rejection of emptiness, then, was not a mistake in the usual sense. It was a reasonable conclusion drawn from limited tools and a commitment to coherence. But as tools improved and observation sharpened, the universe quietly signaled that it was ready to be questioned in new ways. And when emptiness finally became something that could be tested rather than argued, the idea of nothing began its transformation from impossibility to one of the most productive questions in science. For a long time, air and space were treated as the same thing. Both were invisible. Both offered little resistance to movement. Both seemed to exist simply as the background in which objects lived and moved. If a container looked empty, it was assumed to contain nothing of importance. The idea that air itself might be a substance took time to settle, and until it did, emptiness remained poorly defined. The shift began not with grand theory, but with stubborn practical problems. One of the most important came from something as ordinary as lifting water. In the early 17th century, engineers noticed a strange limitation. Suction pumps, used widely in mines and wells, could lift water only to a certain height. No matter how powerful the pump or how carefully it was constructed, the water column would rise and then stop, leaving an empty-looking space above it. This failure was puzzling. If suction worked by pulling water upward, then stronger suction should lift it higher, yet it never did. The limit was consistent, hovering around 10 meters. For decades, this was treated as a mechanical flaw or an inconvenience rather than a clue, but eventually someone decided to look more closely. That someone was Evangelista Torricelli, a student of Galileo Galilei. In the early 1640s, Torricelli proposed a radical idea. Perhaps water was not being pulled up at all. Perhaps it was being pushed. Specifically, pushed by the weight of the air above it. To test this, Torricelli replaced water with mercury, a much denser liquid. Mercury is roughly 13 times denser than water, which meant that if air pressure was responsible, the column should be much shorter. When Torricelli inverted a mercury-filled glass tube into a basin, the mercury fell, leaving an empty-looking space at the top. The remaining column stabilized at a height of about 76 centimeters. The result was striking. Not only did it support the idea of atmospheric pressure, it created something new and unsettling. The space above the mercury appeared to contain nothing at all. No air rushed in. No visible substance filled the gap. Torricelli called it a vacuum. This was not emptiness in a philosophical sense. It was emptiness created deliberately, inside a piece of glass, under controlled conditions. For the first time, emptiness could be pointed to, measured around, and discussed without abstraction. Blaise Pascal took this idea further. If air pressure was responsible for supporting the mercury column, then pressure should decrease with altitude. Pascal arranged for Torricelli's experiment to be repeated at different heights, including the top of a mountain in France. As predicted, the mercury column was shorter at higher elevations, where there was less air above pushing down. These experiments did something subtle but profound. They separated the idea of air from the idea of space. Air was no longer an invisible nothing. It had weight. It exerted pressure. It behaved like a material substance. And if air could be removed, then emptiness was no longer just a word. It was a condition that could be created, even if imperfectly. At the same time, these experiments revealed the limits of what had been achieved. Removing air did not create absolute nothingness. The so-called vacuum above the mercury was not empty in every sense. It was empty of air, but not empty of influence. Light still passed through it. Heat still transferred across it. And whatever occupied that space did not behave like a complete absence. Early vacuum chambers faced similar limitations. Air pumps improved gradually, but none could remove everything. Trace gases remained. Vapor clung to surfaces. Materials released particles slowly over time. Even the best vacuums of the 17th century were only partial. This distinction matters. An empty of air space is not the same as an empty of everything space. The experiments of Torricelli and Pascal did not prove that true emptiness existed. What they proved was something more modest and more useful. Air is not the same thing as space, and removing air does not remove all physical effects. That realization reshaped scientific thinking. If air could exert pressure, then it was a substance. If it could be removed, then emptiness was at least partially achievable. And if emptiness could be created, then it could be studied. There was also an important psychological shift. Once air became something measurable, it lost its status as a placeholder for nothing. It became one more component of the physical world, subject to laws and limits. This freed space itself to be reconsidered. If air was not space, then space might exist independently of whatever filled it. Still, the early vacuums were fragile and imperfect. They depended on glass quality, sealing techniques, and manual pumps. They could not maintain their emptiness indefinitely. Over time, air leaked back in. Surfaces released trapped gases. The vacuum degraded. This imperfection kept expectations in check. No one seriously claimed that true nothingness had been achieved. Instead, the experiments highlighted how stubbornly something seemed to persist. Remove one substance, and another effect remained. Clear away air, and pressure vanished, but light and gravity did not. Emptiness revealed itself not as a final state, but as a layered one. There is a quiet humour in this stage of discovery. Scientists set out to create nothing, only to discover how many different things had to be removed before nothing could even be approximated. Each success revealed another background influence that had previously gone unnoticed. What mattered most was not the degree of emptiness achieved, but the method. Emptiness was no longer dismissed on logical grounds alone. It had become something that could be approached experimentally. This marked a turning point. Questions that had once been philosophical became physical. Claims about nothingness could now be tested rather than debated. By separating air from space, early experimenters opened a conceptual gap. A space could be empty of one thing while still containing others. Emptiness became relative, conditional, and precise. This gap would widen with time, eventually allowing physicists to ask much deeper questions about what remains when matter, energy, and even fields are stripped away. The space above Torricelli's Mercury column did not answer those questions, but it made them possible. Once air was understood as a substance rather than an invisible nothing, a new picture of the universe began to settle into place. Space itself could now be imagined as something distinct from whatever happened to fill it. This separation allowed one of the most influential ideas in physics to take shape, the idea of absolute space. Isaac Newton articulated this view most clearly in the late 17th century. In his work, Philosophia Naturalis, Principia Mathematica, published in 1687, Newton described space as real, fixed, and independent. According to this view, space existed whether anything occupied it or not. It did not depend on objects, motion, or observation. It simply was. In Newton's framework, space was not a substance in the way air or water were substances. It had no texture, no resistance, and no ability to act. Instead, it functioned as a kind of universal reference frame, a perfectly still background against which motion could be measured absolutely. Objects moved through space, forces acted within it, but space itself remained unaffected. This idea solved many problems at once. Motion, for example, could now be defined clearly. An object was moving not merely relative to other objects, but relative to space itself. Acceleration became meaningful even in isolation. A spinning bucket of water, one of Newton's famous thought experiments, could be used to argue that rotation was real even if no other objects were nearby. The curved surface of the water revealed motion relative to absolute space, not merely relative to the bucket. Within this system, emptiness worked beautifully as a passive stage. Remove all matter from a region, and nothing essential changes. Forces still act according to their laws. Objects entering the region behave exactly as expected. Space does not interfere, respond, or participate. It simply allows events to unfold. Classical mechanics relied deeply on this assumption. Newton's laws of motion describe how objects behave under forces, but they say nothing about space itself changing or reacting. Space provides positions, distances, and directions. Time provides duration. Together they form a stable scaffold. On that scaffold, particles move, collide, and interact. This inertness was not considered a flaw, it was a feature. By keeping space silent, physics could focus on what mattered most: matter and force. Calculations became manageable. Predictions became reliable. Planetary orbits could be computed with remarkable accuracy. Cannonballs followed predictable arcs. Tides rose and fell according to gravitational influence. The usefulness of this model cannot be overstated. For centuries it worked extraordinarily well. Even today, classical mechanics remains the foundation for engineering, architecture, and most everyday calculations. Bridges stand, satellites are launched, machines function. All of this depends on treating space as a stable, empty backdrop. There is a certain elegance in this simplicity. Space does not argue. It does not demand attention. It does not complicate equations. It offers a quiet consistency that allows physical laws to shine. In this sense, emptiness was not just tolerated, it was embraced. Yet this silence carried assumptions. By declaring space inert, classical mechanics quietly ruled out certain possibilities. Space could not store energy. It could not transmit influence on its own. It could not change shape or properties. If something happened, it happened because matter did something to matter, mediated by forces that acted across space but did not belong to it. This is where the mechanical view reveals its limits. It treats space as a container, not as a participant. It assumes that removing everything from a region leaves behind nothing of physical consequence, and as long as only solid objects and simple forces were considered, this assumption held. Even gravity, in Newton's formulation, fit comfortably into this picture. Gravity acted at a distance. Objects attracted each other through empty space, but space itself remained unaffected. It carried the force without contributing to it. This was puzzling even to Newton, who famously declined to speculate on the mechanism of gravitational action. But the mathematics worked, and that was enough. There is a quiet practicality to this approach. Physics does not demand metaphysical completeness. It demands predictive success. And the mechanical view of empty space delivered that success repeatedly. Its very silence made it powerful. At human scales, emptiness behaves exactly as this model predicts. A spacecraft drifting between planets encounters almost no resistance. A stone thrown into the air follows a smooth arc. The vacuum inside a laboratory chamber allows experiments to proceed without interference from air. Space, in these contexts, appears to do nothing at all. This apparent inactivity reinforced the idea that emptiness was truly empty. If nothing happens there, then nothing must be there. The absence of obvious effects was taken as evidence of absence itself. But physics advances by paying attention to the quiet details. Over time, questions began to surface. If space is truly inert, how does light move through it? Light is not a material object. It has no mass. Yet it travels at a fixed speed, the same for all observers, regardless of their motion. This behavior sits uneasily within a framework that treats space as a passive background. There are also subtle inconsistencies. If motion is measured relative to absolute space, why does that space never reveal itself directly? Why can it not be detected, pushed against, or disturbed? Newton himself acknowledged this unease, even as he relied on the concept. Still, the mechanical view endured because it worked. Its success delayed deeper questions rather than answering them. And in science, delayed questions are not ignored questions. They wait. The silence of empty space, so useful and so convincing, eventually became something to listen to more carefully. As measurements grew more precise and new phenomena entered the picture, especially those involving light and electromagnetism, the assumption of an inert backdrop began to strain. For the moment, though, emptiness remained obedient. It held still, it allowed motion, it asked nothing in return, and that obedience made it one of the most productive ideas physics had ever adopted. Light has a habit of exposing assumptions. For centuries it behaved just predictably enough to be useful, yet strangely enough to be unsettling. It reflected, refracted, scattered, and travelled enormous distances, often through regions that appeared empty. And as understanding of light deepened, it began to place quiet pressure on the idea that empty space could be treated as nothing at all. In classical mechanics, motion required a background but not a medium. A thrown stone did not need something to carry it forward, but waves were different. Sound waves needed air. Water waves needed water. Vibrations seemed inseparable from the material that supported them, and light, as it was increasingly understood in the 18th and 19th centuries, behaved like a wave. This created an immediate problem. If light was a wave, then what was it waving in? It travelled through space between the sun and the earth, across vast regions where no air could exist. It crossed the apparent emptiness between stars and galaxies. If empty space truly contained nothing, then light had no obvious medium to support its motion. Rather than abandon the wave description, physicists introduced a solution that preserved both intuition and mathematical consistency. They proposed the existence of the luminiferous ether. This ether was imagined as an invisible, all-pervading substance that filled all of space, including regions devoid of matter. It was not air. It had no weight. It offered no resistance to motion. Yet it provided the necessary medium for light waves to propagate. The ether was appealing precisely because it solved multiple problems at once. It allowed light to behave like a wave without contradicting the assumption that space itself was inert. Empty space could remain empty of matter while still being filled with a subtle substance that no one could see or feel. In this way, emptiness was preserved in name, while quietly being filled in fact. Many prominent physicists embraced the idea. James Clerk Maxwell's equations of electromagnetism, developed in the mid-19th century, described light as oscillating electric and magnetic fields. These fields seemed to require a medium in which to exist. The ether fit neatly into this picture. It became the unseen stage on which electromagnetic phenomena played out. But the very qualities that made the ether attractive also made it deeply problematic. It had to be incredibly rigid to support the high speed of light, yet completely undetectable to motion. The Earth, moving around the Sun at roughly 30 kilometers per second, should have been ploughing through this ether constantly. If that were true, then the speed of light measured on Earth should vary depending on the direction of motion, much like the apparent speed of wind changes for a moving cyclist. Careful experiments were designed to detect this effect. The most famous of these was conducted by Albert Michelson and Edward Morley in the late 1800s. Their experiment compared the speed of light along perpendicular paths, expecting to observe slight differences caused by Earth's motion through the ether. The result was unsettling in its simplicity. No difference was detected. The speed of light appeared the same in all directions. Repeated experiments confirmed the finding. If the ether existed, it was behaving in ways that defied explanation. This created a growing tension. On the one hand, the wave nature of light strongly suggested the need for a medium. On the other hand, every attempt to detect that medium failed. The ether was becoming increasingly elaborate in theory and increasingly absent in practice. Light's behavior in empty regions sharpened the problem. Light did not slow down in interplanetary space. It did not scatter or attenuate in ways that suggested interaction with a substance. It travelled vast cosmic distances with remarkable consistency. Whatever space contained, it did not behave like any known material medium. There was also a conceptual discomfort. If the ether filled all space, then space was no longer empty in any meaningful sense. Emptiness had become a semantic illusion. The universe was full, after all, just filled with something conveniently invisible and conveniently unresponsive. This was a subtle shift. Emptiness was being preserved not because evidence demanded it, but because abandoning it felt premature. The ether was doing the quiet work of protecting a familiar picture of space as a passive container. At the same time, light continued to behave in ways that strained this picture. Its speed appeared to be a fundamental constant rather than a property of motion through a medium. Observers moving at different velocities all measured the same value. This was unlike sound, unlike water waves, unlike anything else understood as a vibration of matter. The more precisely light was studied, the less cooperative the ether became. Adjustments were proposed. Perhaps the ether was partially dragged along by the Earth. Perhaps it contracted objects moving through it. These ideas added complexity without adding clarity. There is a gentle lesson here. When a concept exists primarily to protect an assumption, it becomes fragile. The ether existed to protect the idea that empty space must be inert. But as evidence accumulated, that protection began to feel forced. Light did not merely travel through empty space. It seemed to define something about space itself. Its speed set limits. Its behavior revealed structure. It forced physicists to ask whether the emptiness they had relied on was truly as simple as it appeared. By the end of the 19th century, the situation was clear but unresolved. Light behaved like a wave, yet no medium could be found. Empty space seemed to support electromagnetic phenomena without behaving like a substance. The mechanical view of space was under strain, not because it had failed outright, but because it had grown too quiet to explain what was being observed. Light had complicated emptiness without announcing a solution. It had introduced cracks rather than collapse. But once those cracks appeared, the idea that space was merely an empty stage could no longer be taken for granted. Something about space itself was beginning to matter. By the late 19th century, the idea of the luminiferous ether had reached a delicate point. It was widely accepted, carefully described, and increasingly difficult to justify. Light behaved exactly as if it were a wave, yet every attempt to detect the medium carrying that wave came up empty. The question was no longer whether the ether was elegant or intuitive. The question was whether it existed at all. Albert Michelson was one of the physicists determined to find out. Michelson was deeply skilled in precision measurement, particularly in experiments involving light. Alongside Edward Morley, he set out to test a simple and unavoidable prediction. If the Earth was moving through an ether, then that motion should affect how light travelled across the planet. The logic was straightforward. The Earth orbits the Sun at a speed of roughly 30 kilometers per second. If an ether filled all of space, then the Earth would be moving through it constantly. Light travelling in the direction of that motion should take a slightly different amount of time than light travelling perpendicular to it. The difference would be tiny, but not beyond measurement. To test this, Michelson and Morley built an interferometer, an instrument designed to compare the travel time of light along two perpendicular paths. A single beam of light was split in two. Each half travelled down a separate arm, reflected back, and recombined. If the light took different amounts of time along each path, the recombined beams would interfere in a measurable way. The experiment was conducted with extraordinary care. The apparatus was isolated from vibration. Measurements were repeated at different times of day and different times of year, as the direction of Earth's motion through space changed. If the ether existed, the effect should appear somewhere in the data. It did not. The result was not just small, it was effectively zero. No matter how the apparatus was oriented, no matter when the measurement was taken, the speed of light appeared unchanged. There was no detectable sign of motion through an ether. The Earth seemed to move, orbit, and rotate without disturbing any underlying medium at all. This absence was not a failure of sensitivity. The experiment was capable of detecting effects far smaller than those predicted. It was not a matter of poor equipment or careless technique. The expected signal simply was not there. This was deeply unsettling. Physics is comfortable with unexpected results, but it is rarely comfortable with nothing happening when something must happen if a theory is correct. The Michelson-Morley experiment did not merely fail to confirm the ether, it actively undermined it. At first, physicists attempted to save the idea. Perhaps the ether was dragged along by the Earth. Perhaps objects contracted slightly in the direction of motion, cancelling out the effect. These explanations, including those proposed by Hendrik Lorentz and George Fitzgerald, were mathematically clever and physically strained. They explained the result without explaining why it should occur. What made the situation more serious was repetition. Variations of the experiment were performed again and again with increasing precision. The outcome remained the same. Light behaved as if no medium existed. Or more precisely, as if space itself imposed the same rules everywhere, regardless of motion. This forced a re-evaluation of what emptiness meant. The absence of the ether was no longer something that could be dismissed as ignorance or experimental limitation. It was now a consistent, reproducible result. Emptiness was not just what remained when something could not be found. It was what the data actively supported. There is an important distinction here. Science does not treat absence lightly. Failing to detect something once is rarely meaningful. Failing to detect something repeatedly, under conditions where it must appear if it exists, becomes powerful evidence. The Michelson-Morley experiment turned emptiness into a measurable claim. It revealed something unexpected about motion through space. Motion did not seem to be defined relative to a hidden background. There was no preferred state of rest. No invisible substance marked out absolute stillness. Instead, the laws governing light appeared the same for all observers, regardless of how they moved. This was not a philosophical conclusion. It was an experimental one. Space did not behave like a medium. It did not carry traces of motion. It did not provide resistance, drag, or direction. The old idea of absolute space filled with an unseen substance was becoming untenable. What replaced it was not immediately clear. The experiment told physicists what space was not, but not yet what it was. Still, that negative knowledge mattered. The collapse of the ether was not dramatic or explosive. It was quiet. A steady accumulation of null results that refused to go away. There is a certain calm honesty in this moment. Physics did not declare victory. It did not announce a new truth immediately. It simply accepted that a long-held assumption no longer fit the evidence. Emptiness, once treated as a placeholder for ignorance, now demanded to be taken seriously as a physical condition. The failure of the ether also sharpened a deeper question. If light did not need a medium, then perhaps the assumption that waves always require one was wrong. Or perhaps space itself had properties that had not yet been recognized. Either way, the idea of space as a passive, inert backdrop was under pressure. The Michelson-Morley experiment did not solve the problem of emptiness, it transformed it. It marked the point where emptiness stopped being something to fill with convenient substances and became something to understand on its own terms. In removing the ether, The experiment did not return physics to a simpler view. It opened the door to a more radical one, a view in which space and motion could no longer be separated so easily, a view in which the structure of space itself might matter. The silence of the experiment spoke clearly. Whatever space was, it was not a hidden ocean carrying light along. Whatever emptiness meant, it could no longer be dismissed as a failure to look hard enough. It was real, it was measurable, and it was about to demand a completely new description. At the beginning of the 20th century, the problem of emptiness had reached an uncomfortable pause. The ether was gone, but nothing obvious had taken its place. Light travelled through space with unwavering speed. Motion seemed absolute no longer, and the old picture of space as a silent container was beginning to feel inadequate. Into this uncertainty stepped Albert Einstein, not with a new substance to fill space, but with a new way of thinking about space and time themselves. In 1905, Einstein published what would later be called the theory of special relativity. It did not begin with the description of what space is made of. Instead, it began with two deceptively simple principles. First, the laws of physics are the same for all observers moving at constant velocity. Second, the speed of light in a vacuum is the same for all such observers, regardless of how they move. These ideas were not invented to be provocative. They were attempts to take experimental results seriously. The Michelson-Morley experiment had shown that light did not behave as if it were moving through a medium. Einstein accepted this result at face value and followed it to its logical conclusion. What emerged was a radical shift. Space and time, once treated as separate and absolute, could no longer remain independent. Measurements of distance depended on motion. Measurements of time depended on motion. Two observers moving relative to one another could disagree about how long something took, or how far apart two events were, and both could be correct. This was not because measurement tools were flawed, but because space and time themselves were intertwined. Events that appeared simultaneous to one observer might not appear simultaneous to another. Lengths could contract. Clocks could tick at different rates. These effects were not optical illusions or mechanical failures. They were intrinsic properties of reality. To describe this new picture coherently, physicists began to speak of space-time. Space-time is not simply space plus time. It is a unified structure in which distances and durations are linked. An event is no longer described only by where it happens, but also by when it happens. Together, these form a single description. This unification changed the meaning of emptiness. Empty space was no longer just a region without matter. It was a region with a specific space-time structure. Even when nothing occupied it, space-time still existed. It still had measurable properties. It still constrained what could happen within it. One of the most striking consequences of special relativity is that empty space now imposes limits. The speed of light acts as a universal maximum speed, not because light struggles against resistance, but because space-time itself is structured in such a way that this speed cannot be exceeded. This limit exists even in perfect vacuum. Even in the absence of matter, space-time enforces rules. This alone is enough to show that emptiness is not nothing. A region that restricts motion, defines simultaneity, and links space to time is not inert in the classical sense. It may not be filled with particles, but it is not passive. Another profound shift followed naturally. If space and time are intertwined, then measurements depend on the observer. Emptiness, once assumed to be absolute, becomes relative. Two observers moving differently through the same region of space-time may not agree on its dimensions or duration. The space between 2 points can be shorter for one observer and longer for another. The time between two events can stretch or compress depending on motion. This does not mean reality becomes subjective. The underlying space-time structure remains consistent. What changes is how that structure is sliced into space and time by different observers. Emptiness has geometry, but that geometry is not experienced identically by everyone. This idea can feel unsettling, but it is grounded firmly in experiment. Time dilation has been measured using precise atomic clocks flown on aircraft and satellites. Length contraction plays a role in the behavior of fast-moving particles in accelerators. These are not abstract predictions. They are practical consequences of space-time structure. Einstein's work also quietly resolved a lingering discomfort from classical mechanics. Absolute space, which could never be detected directly, was no longer needed. Motion no longer had to be measured relative to an invisible background. Instead, motion was defined relative to other observers, all governed by the same physical laws. This did not make space disappear, it made it richer. Space became part of a dynamic framework rather than a silent container. Even in the absence of matter, space-time retained its structure. It defined what paths were possible. It determined how clocks behaved. It shaped the behavior of light. There is a gentle irony here. In removing the ether, physics did not return to emptiness as nothing. It replaced one unseen medium with a deeper, more abstract structure. Space-time does not behave like a substance, but it is not nothing either. It can be measured, modelled, and tested. It has geometry. It has limits. It has consequences. This new view also softened the question of emptiness rather than answering it outright. Asking whether space is empty now requires asking empty of what? Empty of matter, perhaps. Empty of energy, not necessarily. Empty of structure, certainly not. Special relativity revealed that even a perfect vacuum carries information about motion and causality. It defines which events can influence which others. It determines how signals propagate. It encodes relationships that exist regardless of whether particles are present. In this sense, emptiness becomes contextual. A region may be empty of atoms yet full of space-time relationships. It may contain no particles, but still enforce cosmic speed limits and temporal order. This was only the beginning. Special relativity reshaped how motion and time were understood, but it left gravity untouched. Gravity, still described by Newton as a force acting through space, remained awkwardly separate. If space-time defined motion, then gravity's role within that structure demanded rethinking. Einstein would not leave that problem alone for long. The realization that space and time form a unified entity opened a new possibility. If space-time could define motion, perhaps it could also respond to matter. Perhaps emptiness itself could be shaped. The quiet revolution of special relativity did not make space noisy or dramatic. It made it meaningful. Empty space was no longer a void waiting to be filled. It was a framework with rules, limits, and geometry. And once that framework existed, the idea that gravity might be a feature of space-time itself became not just possible, but inevitable. Emptiness had acquired structure, and with structure came the possibility that it could bend, stretch, and change. Once space and time were understood as a unified structure, one long-standing problem refused to stay quiet. Gravity still did not fit. In Newton's picture, gravity was a force acting across empty space, pulling objects toward one another without contact. It worked extremely well mathematically, but it sat awkwardly beside the new understanding of space-time. If space and time defined motion itself, then gravity seemed oddly external, as if it were acting on space-time without belonging to it. Albert Einstein took this tension seriously. Over the course of 10 years, from 1905 to 1915, he reworked the foundations of gravity entirely. The result was the theory of general relativity, a description of gravity that did not treat it as a force moving through space, but as a property of space-time itself. In general relativity, matter and energy influence the geometry of space-time. Massive objects do not pull other objects toward them in the traditional sense. Instead, they alter the shape of space-time around them. Objects then move along the natural paths within that curved geometry. What appears as gravitational attraction is actually motion guided by the structure of space-time. A common way to picture this involves imagining a stretched surface with a heavy object placed on it, causing the surface to dip. Smaller objects roll inward not because they're pulled, but because the surface beneath them slopes. While this analogy is limited, it captures the essential idea. Gravity is not something added on top of space. It is how space itself is shaped. This shift has profound implications for emptiness. In Newtonian physics, empty space was flat, uniform, and inert. In general relativity, empty space can be curved. Geometry no longer depends solely on the presence of matter at every point. It can exist independently, carrying information about past and distant influences. This is one of the most counterintuitive aspects of modern physics. A region of space can be empty of matter, and yet still possess curvature. That curvature can influence motion, bend the paths of light, and shape the behavior of objects passing through, even if nothing occupies the region itself. This idea is not hypothetical, it is observed. Light passing near massive objects bends, a phenomenon known as gravitational lensing. This effect was first confirmed during a solar eclipse in 1919, when stars appearing near the sun's edge were observed to shift position. The light was travelling through space that was empty of matter, yet its path curved because space-time itself was curved by the sun's mass. Even more strikingly, general relativity allows for solutions in which space-time curvature exists entirely without matter. These are known as vacuum solutions to Einstein's field equations. The equations governing space-time do not require matter to be present everywhere for curvature to exist. They allow geometry to propagate and persist on its own. Gravitational waves are a clear example. These are ripples in space-time itself, produced by accelerating masses such as merging black holes or neutron stars. Once created, these waves travel outward at the speed of light, passing through vast regions of empty space. They stretch and compress space-time as they move, even where no particles are present. Gravitational waves were directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, confirming a century-old prediction. What was detected was not matter, not radiation, but a change in space-time geometry itself. Empty space was actively oscillating. This reveals something subtle but essential. Emptiness, in general relativity, is not defined by flatness. It is defined by the absence of matter and non-gravitational energy. Geometry remains, structure remains, rules remain. This is why gravity in this framework is not a force inside space, but a feature of space. Objects respond to geometry rather than being pulled through a void. Free-falling objects follow the straightest possible paths through curved space-time, paths known as geodesics. These paths exist whether or not the region contains matter. There is a quiet elegance to this idea. Gravity becomes less like an invisible hand and more like the shape of the landscape. Space tells matter how to move, and matter tells space how to curve. But once the curvature exists, it does not vanish when matter leaves. It carries history. This challenges the intuition that emptiness must be simple. An empty region near a star is not the same as an empty region far from all mass. Both may contain no particles, but their geometries differ. Light behaves differently. Time passes at different rates. Motion unfolds along different paths. Even time itself becomes uneven. Clocks placed at different positions in a gravitational field tick at different rates, a phenomenon known as gravitational time dilation. This effect has been measured repeatedly and must be accounted for in technologies such as the Global Positioning System. Once again, empty space proves capable of influencing physical processes. There is a gentle irony here. The more physics removes matter, the more space itself steps forward. What began as an empty stage becomes an active structure. What was once assumed to be nothing turns out to be the very thing shaping motion, light, and time. Importantly, general relativity does not claim that space is filled with a hidden substance. It does not revive the ether in a new form. Space-time curvature is not a material medium. It does not provide resistance. It does not define a preferred frame of rest. It simply has geometry, and that geometry matters. This distinction preserves the lessons of earlier experiments. There is no absolute background against which motion is measured, yet there is still a real, physical structure governing how events unfold. Emptiness is neither a void nor a substance. It is a geometric condition. At this point, the idea of empty space has changed completely from its original meaning. It is no longer defined by the absence of influence. Empty space influences motion. It shapes trajectories. It limits possibilities. It carries waves. And still, something is missing. General relativity describes geometry beautifully, but it says little about energy in regions completely devoid of matter. It treats space-time as shape, not as a reservoir. The question of whether empty space contains energy of its own remains open at this stage. Curved space can exist without matter, but curvature itself may carry something more subtle. The geometry of emptiness is established, but its energetic content has not yet been fully addressed. Emptiness, now undeniably structured, quietly invites the next question. If space can bend and ripple without particles, can it also store energy without them? And if so, what kind of energy would that be? The stage is no longer silent, but it is not yet finished speaking. By the time gravity had been reimagined as geometry, another quiet revolution was already woven into the fabric of physics. Long before space-time was curved, space itself had begun to acquire occupants that were neither particles nor substances. These occupants were known as physical fields. A field is not an object you can hold. It is not a material that flows or accumulates. Instead, a field assigns a value to every point in space and time. It describes what would happen if something were placed there. A magnetic field tells you how a compass needle would turn. An electric field tells you how a charged particle would accelerate. Even when no particle is present, the field still exists. This idea was most clearly developed in the 19th century by Michael Faraday. Faraday was not primarily a mathematician. He thought visually and experimentally. He introduced the concept of lines of force, imagining space itself threaded with invisible structures that guided electrical and magnetic effects. To Faraday, these lines were not just helpful drawings, they were real features of space. This was a radical step. Instead of forces acting instantaneously across empty space, influences were carried locally by fields that filled the region between objects. Space was no longer just the place where interactions happened. It became the medium in which those interactions were encoded. James Clerk Maxwell took Faraday's intuition and gave it mathematical form. In the 1860s, Maxwell unified electricity and magnetism into a single framework, now known as classical electromagnetism. His equations show that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. Together, they can sustain one another, forming electromagnetic waves. Light itself emerged naturally from this picture. Maxwell's equations predicted waves that travelled at a fixed speed determined by electric and magnetic properties. That speed matched the measured speed of light. Light was no longer a mystery substance or a mechanical vibration. It was an oscillation of fields. Crucially, these fields did not require particles to exist. An electromagnetic field can occupy a region of space, even if no charged particles are present there. The field is not created anew each time a particle passes through. It already exists as a condition of space itself, shaped by boundary conditions and sources elsewhere. This has an important consequence for emptiness. A region of space can be empty of matter and still contain fields. Those fields can store energy, transmit influence, and affect anything that enters the region later. Empty space in this sense is already structured before anything arrives. Field energy is not abstract. It can be measured and accounted for. An electric field between two charged plates stores energy that can be released. A magnetic field carries energy that can exert pressure. Even in regions far from any source, residual fields can persist. This shifts the meaning of emptiness yet again. Removing particles does not remove structure. It does not return space to a neutral background. Instead, space retains a pattern of possibilities. It defines how particles would behave if they were present, even when they are not. There is a gentle clarity to this idea. Fields do not demand attention. They are not loud. They do not clutter space with objects. They simply exist. Everywhere they are allowed to exist, quietly defining the rules of interaction. In classical physics, fields were treated as continuous quantities. Their values changed smoothly from point to point. They could be strong or weak, curved or straight, but they did not come in discrete pieces. This continuity made them feel less like objects and more like conditions, and yet their presence was undeniable. Without fields, forces had no mechanism. Without electromagnetic fields, light had no description. Without gravitational fields, motion lost its guide. Fields became indispensable. This also resolved a lingering discomfort. Forces no longer had to leap across empty space instantaneously. They could propagate at finite speeds through fields that occupied the intervening region. Space was no longer empty between interacting objects. It was filled with the very structures that made interaction possible. At the same time, fields did not behave like the abandoned ether. They did not define a preferred state of rest. They did not resist motion uniformly. They were compatible with relativity. Their behavior depended on observers, but their existence did not privilege any particular frame. This compatibility mattered. It allowed fields to coexist naturally with the space-time picture introduced earlier. Fields lived in space-time. They evolved over time. They respected the limits imposed by the speed of light. They fit. Still, classical fields carried an implicit assumption. They were smooth, continuous, and infinitely divisible. At every point, a value could be defined with arbitrary precision. This assumption would not survive indefinitely. As measurements became more precise and scales became smaller, cracks appeared. Energy exchanges occurred in discrete amounts. Light behaved like both a wave and a particle. Fields, once thought to be smooth fabrics, began to show grain. But before that transition, fields performed a crucial role. They established that empty space is not empty of physical content. It is filled with conditions, structures, and stored possibilities. Even without matter, space is already busy defining how matter will behave when it arrives. This makes fields a natural bridge between classical and quantum thinking. They retain the continuity and calm of classical physics, while quietly preparing the ground for something more restless. They show how structure can exist without substance, how influence can persist without objects. By the time particles are removed, something always remains. Geometry remains. Fields remain. Rules remain. Empty space, once imagined as a blank canvas, has become a textured one. Not crowded, not noisy, but undeniably present. And with fields occupying every region where physics allows them to exist, emptiness takes on a new character. It is no longer the absence of everything, but the presence of what cannot be seen. This realization does not yet require quantum mechanics. It simply requires accepting that space itself carries more than location. It carries information, structure, and stored influence. And that acceptance quietly sets the stage for the next transformation. By this point, emptiness has already lost much of its original simplicity. Space can curve. Fields can exist without particles. Geometry can guide motion even where nothing tangible is present. But one idea still resists intuition more than most. The idea that energy itself can exist without objects. In everyday experience, energy feels inseparable from things. A moving car has energy because it has mass and speed. A hot stove has energy because its atoms are vibrating. A stretched spring stores energy because it can snap back. Energy seems always tied to matter doing something. This intuition is useful but incomplete. In physics, energy is not defined by objects alone. It is defined by the capacity to cause change. Anything that can influence motion, temperature, structure, or interaction is said to carry energy, whether or not it is attached to a solid object. Fields make this clear almost immediately. An electric field stores energy even if no charged particle is moving through it. A magnetic field can exert pressure, transfer momentum, and do work. That energy does not vanish simply because the field is temporarily empty of particles. It remains distributed throughout space. This is not a metaphor, it is measurable. The energy stored in an electric field between charged plates can be calculated and released. The energy density of a magnetic field can be detected through its effects. Space itself, structured by fields, becomes a reservoir. Gravity adds another layer of subtlety. In general relativity, gravity is geometry rather than force, which makes gravitational energy difficult to localize. There is no single point where gravitational energy sits. Instead, it is associated with the curvature of spacetime as a whole. Despite this difficulty, gravity clearly carries energy. Gravitational waves transport energy across the universe. As they pass through space, they stretch and compress distances, doing work on anything they encounter. Detectors on Earth have measured this effect directly. The energy arrives not as particles, not as radiation, but as changes in space-time itself. What matters here is not the bookkeeping challenge, but the implication. Empty space, shaped by gravity, can carry energy without containing matter. The energy is not stored in objects, It is stored in structure. This challenges everyday logic because human intuition evolved in a world where energy was always attached to something visible. Fires burned fuel, muscles burned food, rivers flowed downhill. Energy appeared only when matter moved or transformed. Physics reveals a broader picture. Energy can be spread out, it can be diffuse. It can exist as tension, curvature, or configuration. It does not need a container in the ordinary sense. This becomes especially clear when considering gravitational binding energy. When two massive objects attract each other, the system as a whole has less energy than the objects would have if they were infinitely far apart. That difference is energy associated with the gravitational field between them. Remove the objects, and the energy accounting changes. But while they exist, the energy is not sitting inside either object alone. It belongs to the space between them. Fields behave similarly. An electromagnetic wave traveling through empty space carries energy and momentum. It can heat surfaces, push objects, and trigger chemical reactions. That energy exists while the wave passes through regions containing no matter at all. At this stage, emptiness no longer looks passive. Even stripped of particles, space remains capable of storing, transmitting, and redistributing energy. It can act. This is not a violation of conservation. Energy is still conserved. It is simply not confined to objects. Conservation laws apply to systems that include space itself as a participant. There is a quiet shift in perspective here. Instead of asking where the energy is stored, physics asks how energy is distributed. That distribution often includes regions that appear empty. This shift also explains why emptiness resists being fully cleared. Removing matter removes one carrier of energy, but it does not remove fields, geometry, or motion itself. Each layer peeled away reveals another layer beneath it. There is a temptation to imagine that once matter is gone, nothing meaningful remains. Physics consistently refuses this simplification. Even when particles are absent, the conditions that define how particles will behave remain in place. Those conditions have energetic consequences. This does not mean that empty space behaves like a battery waiting to discharge. It means that space participates in physical law. It enforces limits. It carries influences. It responds to change. At larger scales, this idea becomes unavoidable. The expansion of the universe involves energy associated with space itself. Gravitational waves cross cosmic voids. Light travels for billions of years through regions nearly devoid of matter, carrying energy the entire time. At smaller scales, the same principle applies. Even before quantum mechanics enters the picture, classical physics already demands that emptiness be energetically active. This realization unsettles a simple mental shortcut. The shortcut says that energy requires stuff. Physics replies that energy requires structure, and structure does not vanish when matter does. There is a certain calm honesty in this. Nature does not make special allowances for intuition. It follows consistent rules whether those rules feel comfortable or not. Emptiness, as it turns out, follows rules too. By now, empty space has acquired geometry, fields, and energy. It is no longer reasonable to think of it as a void. It is a participant, even when it appears still. And yet, everything described so far remains within the framework of classical physics. Fields are smooth, energy can be continuous. Space, while structured, behaves predictably at every scale considered so far. This calm will not last indefinitely. As attention turns towards smaller scales and higher precision, a new kind of restlessness appears. Energy exchanges become discrete. Fields begin to fluctuate. Emptiness itself starts to exhibit activity that cannot be smoothed away. The idea that energy can exist without objects is not the end of the story. It is the threshold. Once energy is allowed to exist independently of matter, the question naturally follows. If energy is allowed everywhere, even in emptiness, what prevents it from appearing, disappearing, or fluctuating at the smallest scales? That question belongs to quantum mechanics, and once it is asked, emptiness becomes something far stranger than a quiet background.